Welcome back, Chemistry 30. This is the EC1.5 cell potentials and spontaneity under standard conditions section. We'll look at more or less cell potentials in this one. Then we'll look at spontaneity kind of in the next section. I sort of mention it here, but we'll continue it on in the final section immediately right after this. All right, so we're going to predict the electric potential of various redox reactions using reduction potentials. We'll see what that is in a bit. So why do electrons transfer spontaneously from a zinc atom to an ion, either directly through an external circuit as seen earlier? So we saw that earlier, zinc automatically breaks down into ions and gets rid of the electrons. In simpler sense, we can compare the electron flow to the flow of water in a waterfall as seen in the figure below. So back in Science 9, you may have talked about this in terms of electricity, and kind of related it to a waterfall. So here we have high stored energy, here we have low stored energy. So high potential energy, low potential energy. You kind of think of this as the negative pole of a battery where there is tons of electrons sitting, and on the opposite side where it's positive, we could think of there's a deficiency of electrons. So electrons want to go from a high potential to a low potential, just like a waterfall, going from a high potential to a low potential. And of course over here, the negative region is called the anode, because remember, lose electrons oxidation. We can kind of think of it as this, Leo anode, almost sounds like a name. Leo anode, lose electrons oxidation, that occurs at the anode. And at the cathode is where we have cathode. So for that, you can kind of think of what says cat. Cat says so that's where the electrons want to go, and that is positive. Kind of imagine it like a cat mouth almost. There we go. So looking at this, water flows spontaneously over a waterfall because of a difference in potential energy between the top of the falls and the bottom. In similar fashion, electrons flow spontaneously through an external circuit from the anode of an electrochemical cell to the cathode. Okay, so the anode to the cathode. It's interesting because we think of this as cations, right? Anions and cations. But when we think about a battery, think of it as the anode is where loss of electrons happens. Lose electrons oxidation. It's kind of tricky to remember those. Because of a difference in potential energy, the potential energy of electrons is higher in the anode than in the cathode. Thus, electrons flow towards the electrode with the more positive electron potential. So we go from that electron sufficient area to the electron deficit area, or the area in which we don't have a lot of electrons. The difference in potential energy per electrical charge is referred to as potential difference between the two electrodes, and we measure that in volts. 1 volt is the potential difference required to impart 1 joule of energy per 1 coulomb. Because back we would have taken V is equal to W over Q, so work per time. Work is measured in joules, charge is measured in coulombs, so that's where we get joules per coulomb, and we can shorten that into 1 volt. The potential difference between two electrodes of an electrochemical cell is called the cell potential, denoted E with the subscript cell. Because the potential difference provides the driving force that pushes electrons through the external circuit. We also call it electromotive force. Electromotive means causing motion. So electrons causing motion. So electromotive force, or EMF, sometimes it's referred to as. Because E cell is measured in volts, it is commonly referred to as the voltage of the cell. The cell potential of any electrochemical cell is positive. So when going through this, if I was to hook this up, I would see we consider that to be positive voltage. The magnitude of the cell potential depends on the reactions that occur at the cathode and at the anode, and the concentration of reactants and products, and the temperature, which we'll look at in a bit. And that temperature is assumed to be at 25 degrees C, unless otherwise noted. In this section, we'll focus on cells that operate at 25 degrees C under standard conditions. So we assume that's 25 degrees C with a certain concentration, etc. The cell potential under standard conditions is called the standard cell potential, or standard EMF, denoted E cell. So this little circle up here indicates standard conditions. So we can almost do this, put a little arrow from standard conditions pointing to that raised circle there, that's superscript. For the zinc copper electrochemical cell seen earlier, the standard electron potential is plus 1.10 volts. So we have solid zinc in contact with copper ions. What happens here is we get a replacement here, and zinc ions float around and copper solid is made. The superscript E cell indicates standard conditions. So yes, that raised circle there. Standard reduction potentials. The standard cell potential of an electrochemical cell, E cell, depends upon the particular cathode and anode half cells. We could in principle tabulate standard cells for all possible combinations. However, it's not necessary to undertake this arduous task. Rather, we can assign a standard potential to each half cell and then use these half cells to determine the E cell overall. The cell potential is the difference between the two half cell potentials. By convention, the potential associated with each electron is chosen to be the potential for the reduction. So we look at these in terms of what happens with reduction. And one of the sheets you'll be getting is a list of tons of different ones that we have here. And notice all of them are in the form of reduction. So everything is adding electrons, adding electrons, adding electrons. So gaining electrons to make something. All right? So we often refer to it as reduction. Thus, standard half-cell potentials are tabulated for reduction reactions, as you've seen in that sheet, which means they are standard reduction potentials. So we can symbolize that as E subscript red for reduction. Standard cell potential E cell is the standard reduction potential of the cathode reaction minus the standard reduction potential at the anode. So we're taking a look at, so if we have our battery, or we'll just use a battery for example for now. So you have a negative side, the anode, and the cathode. So going from here to here, so we have at the cathode we have reduction because it's gaining electrons here. And over here at the anode, we have electrons leaving the solid and moving from here to here. So we look at the cathode to anode. So from cathode to anode. So kind of like final minus initial, like we always do with the change in. The final area versus initial. It's usually common practice to draw it such the anode is on the left and the cathode's on the right too. That's something that you usually see done in textbooks or in drawings. So final minus initial, so the reduction potential at the cathode minus reduction potential at the anode. It is not possible to measure the standard reduction potential of a half cell directly. If we assign a standard reduction potential to a certain reference half reaction, however, we could determine the standard reduction potentials for all of them. So we look at what do these happen with a certain standard, and that standard is used with the half reaction of hydrogen ions going to hydrogen gas molecules. Under standard conditions, this is considered to be a value of exactly 0 volts. So hydrogen ions picking up electrons to become the hydrogen molecule. An electrode designed to produce this half reaction is called a standard hydrogen potential, or hydrogen electrode, or a SHE for standard hydrogen electrode. And this standard hydrogen electrode consists of a platinum wire connected to something. So if we look at the next page, platinum wire connected to a piece of platinum foil, which is considered unreactive, which is covered with finely divided platinum that serves as an inert or an unreactive surface for the reaction. So we, instead of having something that's going to be consumed or added to in the reaction, we have a platinum wire where the reaction will still happen, but it won't be consumed as a result. So if we look at reduction here, we have a platinum ion, we have hydrogen ions, electrons from the platinum ion hit that hydrogen ion and make the hydrogen molecule. or vice versa. Oxidation, we have a hydrogen molecule which can come here and cause its electrons to leave. Then you have H plus ions going to solution. So notice that they don't get added on to the platinum itself. The standard hydrogen electrode allows the platinum to be in contact with both the 1 molar hydrogen ion and a stream of hydrogen gas at 1 atmosphere. The standard hydrogen electrode can operate as either an anode or a cathode, as we saw up here. So it can either provide electrons to an ion to make a molecule, or if a molecule is close to it, it can take its electrons away and make that molecule form ions in solution. So that's the interesting thing about that. It can act as either one. The figure below shows an electrochemical cell using a standard hydrogen electrode. The spontaneous reaction is the one shown earlier, the oxidation of zinc and the reduction of hydrogen. So over here, so with this half reaction, we have solid zinc going into ions in solution, so it's breaking down, and its electrons maintained on this bar, and they're going to go up here. And over here we have a hydrogen gas inlet. So what we have over here, of course, is picking up those electrons via the hydrogen ions in solution. And we have hydrogen gas being formed. So picking up those electrons by the hydrogen ions and making molecules. So over here we have now it says showing this hydrogen going in, but I believe the hydrogen is going out because that's what's being formed here. Hydrogen ions pick up the electron. Each hydrogen ion picks up an electron, or 2 picks up 2, making, the reason why we have 2 and 2 is because hydrogen gas is a diatomic molecule, H2. All right, I think I'll do is I'll stop the video there, and then we'll come and look at part 2.